Hello everyone, this is Codyssi day 14, and um, we are recording this late. Let's go. A lot of text. So we have some items. There's a lot of text parsing. Mm. What is this sound? What is this sound? So annoying. So Each of the so these are the items. We can make tuples is equal to int of while dot split of this of one of, okay, and then the same but for the other things. Oh, is it going to be a knapsack? So you have to find the highest quality combination of items that can be synthesized with 30 units. Okay. Where's the least unique materials to synthesize? Optimal. Okay. So is it already an knapsack? Right, these are they all have a very high cost. Like many of those pairs just cannot be done. It feels like quality cost. Yeah, they all have a very high cost. It can be difficult too if it's already an knapsack. Is there an easier way to do this? I can pair this with these two, these three is 4. Should we do this in quadratic time? I think I'm going to implement an knapsack. So we have a cost. We have basically a total budget of 30, and we need to find the highest quality. So what we can do is do an knapsack with no repetition. Okay, so this is a knapsack with no repetition. We have to find, the thing is that here we can, is it just pairs or no, we can do, but I mean, I can implement knapsack, but it's weird because this is difficult too. So I'm thinking if there's an easier solution to this, but I think we're gonna get to knapsack at the end of the day, so I'm just gonna implement it now. So knapsack works that we need to so we have some items and we have a cost. So let me just check it really quickly. Knapsack problem DP. We have the items, so the weight here, and so is this the total weight? Yes, so this is the max weight, and these are the items sorted. Right. Or what we can do is we can even try to do it recursively. If it's not, there's a lot of stuff here though. Let's try to do this recursively. Okay, so what we're gonna do is this. So we have, so we don't care about this. So we have we don't even care about this. Well, I think that if we, no, let's don't do this. Okay, so let's just print data. So we have, oh geez, what did I do? Okay, so not data, but its. So we have tuples here. So now we are only interested basically in those. So let's do this. So def search, well, def db. So let's do best weight. So this takes the list of items, the sort of avail, so left, so the items left, it takes the current weight, and it takes current weight and the already taken items, so taken. So what we can do is we can do taken starts from empty. Let's just do this brute force. So pass this. But we only needed the best. So we could actually so let's do, so if the weight is 0, then we return, so these are the items left, the current weight, the taken items, and so the weight is the current weight, okay? So we're gonna return, so if weight is 30, because we can either take or not take the item, right? So we can go, we also need the item that we're on. So we don't need items left in this case. We only just items. So just like items, all items. Okay, so if the current weight index is equal to the len of all items, then we return the current weight. In this case, we return the weight. Otherwise, so and if the weight is exactly 30, so is this the weight that we have in our bag? So this is the weight we already have. So if weight is 30, then we can return, well, we also need the value, right? We also need the current value. So we don't return weight, but we return value. And here we return value as well. So let's do or weight is 30, then we return the value. Otherwise, we can just try to take or not take the item. So what we can do is we just say return the max. So +1 is best weight. We do all items. The weight is so we have weight. What is it? Is quality cost maths. So qual cost maths is all items of index. So in this case, we only care for now about the items. The weight is weight plus well, we can also do this. So if weight is greater or equal than is, let's say, greater than 30, we can return float inf. This way we will never take this. Oh, sorry, minus inf. So we don't care about, so we just do this. Let's wait, so we can just try to take it. So weight plus like cost, and the taken is, we don't care too much about taken right now. Let's just care about the stuff. So we don't care about this. Index +1, and the value is value plus qual, right? And pos2 is the same, but we still go index +1. We don't increase the weight and we don't increase the value. Return max between pos1, pos2. And this should work for small inputs. So print, so all items, though it's not a list, it's a dictionary. So we have to convert this to a list. So we can do all items is just val for k. Oh, it's just list of its dot items dot values. So we just do print best weight, all items weight. So all items, the weight is initially 0, the index and the value. The index is 0, the value is 0. 121. Total quality here is 86. Are we correctly adding the quality here? So value plus qual, yes. It's a little bit too much. Let's do taken. It's just a string. So Because here we don't have. Oh, fuck. No, let's just. Let's do this. Let's just put the ed here. It's like ed. Pos1 is greater than pos2, then you can say return what? here. Okay, so there's too much weight there. It's here. Total number of unique materials needed is 96, and we have to do that. Okay, so in this time maths is 0 to this. Maths is still taken. Total weight is maths. Sorry, it's still, but it's like 1, 2, 3. Sorry, 2. What the fuck? Okay. Print maths by bal. Or what? This is maths here. Maths. Jeez. Maths. 8256. Yeah, it's correct, but we have a bug. in the sense that we need to say that we have to take the one. So the optimal combination is, there is a tie, choose the combination that requires least amount of unique materials. So what we're going to do is we're going to do that. This is pretty bad, but so elif pos1 is equal to pos2. Then we take the one with less materials. So maths1 is something, or we can keep track of the maths also. Let's keep track of the maths needed. Maths needed is 0. And what we do is, here we also need to keep track of the maths needed, sorry, M1 and M2. And here we do like maths, let's call this maths. Let's call this maths is equal, like maths plus maths. This is already maths, so maths for now. So it's maths for now plus maths, and here is nothing, and we don't need yes, so we need maths for now or that. Here we got nothing. M1 and M2 are those. So in this case, so no, we don't care. We don't need to return it. Just return. So if M1 is M2, return +1. Sorry, this, so we return +2 in this case, and else return +1 here. Okay, so we need to +1 and 1 and 2. Value taken for now, and here it's just float if too many values to unpack. File taken maths. So in this case, we don't even need this. Total weight, but wait, total quality, we don't need the total weight. This, part 3. So it's the same. We just have 300 units. So we need to optimize this a lot. So let's just add memo. If memo of weight index value taken, we don't need maths for now, we need so if this is in memo, then we do return memo of this. Otherwise, I think the answer will just be the weight and the what we store in memo is just, we can store everything actually. Don't care about this. One. Yes. We do the same. Sì, un attimo mamma. Sì. This is post 2, path 2 and 2. This is post 1, path 1 and 1, that's right. This is post 2, path 2 and 2. And then we return it. And this needs to be a tuple. This has to be this, this, and this. So we'll take the slice. slow. How to optimize this? Mm, can we throw away some states? We can like, not sure if we can throw away some states. Do we throw away some shit? Really fast. I guess one thing that we can try is just try to remove from memo the maths for now thing. Hmm. Let's go. Okay, so this is a very good example of how sometimes you have to just attempt some things. So what's happening here? So let me get back here. So basically in part 3, so part 1 is just parse the input and do some stuff. Part 2 is knapsack problem. Okay, so knapsack problem, we have some items. Each item has a cost and has a quality. So in the knapsack problem, the cost is the weight and the quality is the value. And then we also have another unique materials stat, which is basically just a thing that just solves the ties. So if two set of items have the same uh, quality and same cost, then we have to take the one with the obviously the lesser number of unique materials. Then for part 3, I guess. Okay, so this is, as I said, knapsack problem. And here we have a total weight of 30. And it's actually a very low weight. So what I did is I implemented a recursive solution. And even without here, obviously I forgot to copy the to copy the B problem to save the part B, but um, even without the memoization, so only with a recursive function, this thing works. So ignore the memo for now. So what happens is that you just save, like your state is the weight, the weight, current weight that you have, the index that you're at, the value, so the value that you accumulated up to now, the taken items, this is not needed, but it's just for debugging purposes, and the maths for now, so the total number of materials that you accumulated for now. And basically, index means the item that we are at. So when I am on an item, I can either take it or not take it. If I take it, then I just go to the next item, and add the quality, so add the quality to my current value. And I also have to take the, what is this F here? F is, yeah, F is the, this is the taken plus F. Okay, so these, okay, this is the, sorry, this is the ID of the item. So this is just, as I said, for debugging, and then we add the maths. Otherwise, we don't do it. So we just go on, skip the item, and just keep our stats. And then here I just solve the ties by checking the materials. So what I noticed is that so part 2 is fine. Recursive, all of this stuff, the state is this, and it's fine. So all items is just a reference to our item set. For part 3, basically it's the same problem, but we have a bigger cost. So in this case, we have a cost of, sorry, we have a bigger total weight. So before we had a weight of 30, now we have a weight of 300. So what I assumed here is that with 300 weight, so with a weight of 300, it's very hard that two item sets will have the same weight and the same value. So that with this assumption, what I did is I just removed from the state the maths for now. So basically here, as you can see, when I memoize the states, I just don't memorize the maths for now. And here I just cross my fingers and just hope that there was no tie in the final answer. And that's actually what happens. Actually, I also tried with the test, sorry, the test input, and also for the test input it works. So also with 150, we get the same answer as the the description. So this is a good enough optimization, and this time you don't. This is obviously a lazy solution, because this wouldn't work if if we had actually ties on the final answer. So if you want to write a good solution for this, you have to use either a faster programming language, probably with C++. In this case, you probably wouldn't even needed the memoization, maybe. I don't know, maybe with C++ you don't need the memo for part 3. I'm not sure about that. I'm really not sure. I should try. But for sure, if you add memoization in C++, you can definitely keep track of also the maths for now in the state, and it would cause no problems in terms of time execution. Another thing you can do is just write a bottom-up DP. So the bottom-up DP works, it's like the first thing that I thought about, but I was a little bit rusty on bottom-up DP for the knapsack problem, so I didn't really write it. But what you can use, you can just look for knapsack problem DP, and basically it's like this. So you have a table, you have the weight on the columns and the items on the rows, and then you just go down and fill the table in linear time. So obviously linear in terms of like this table grows with the total weight that you have. So with a weight of 300 is a table with 300 columns and a number of rows, which is the number of items. So it's actually a big table, but it's way faster to fill this table than doing a exponential time search as I did. So yeah, here with like if you wrote bottom-up DP for part 2 already, you just plug in the value in part 3 and it was like 2-second answer. So yeah, nice problem today. So definitely a nice problem. I will probably in the later days write a bottom-up solution for Python or maybe in C++. I'm not sure. But just to get back on bottom-up DP, which is something that I should definitely revise a little bit. Okay, so see you tomorrow.